Hello friends. In the previous lectures, we'll be considering a specific form of ODEs. So these ODEs we refer to as the linear ODEs. The characteristic feature of this linear ODEs is that the derivative of this function is proportional to the function itself. So in this case, in such a case, we refer to it as the linear ODEs. Ultimately, they lead to a linear relation. So therefore, we refer to as the linear ODE. And the example that we considered, it involved the nucleation rate, a specific heterogeneous nucleation rate. And this is proportional to the nucleation rate is proportional to the number of nuclei that is present in a system at a given time t. So this is the specific example that we considered, and this is the generalized expression of it. Now in the previous lecture, we considered first order linear ODE and also the second order linear ODE. We considered certain approaches that can be adopted to solve these ODEs. Besides the analytical treatment, we also saw some approximation techniques that can be adopted to solve these ODEs. So we saw linear first order and we also saw linear second order ODEs and the approximation technique that can be adopted to solve both first order and second order. The approach that we adopted to solve the second order ODE can also be extended to solve the higher order ODEs as well. Now in this lecture, we will be relaxing our consideration, or we'll be moving away from our consideration of the linear ODE, and we will try to arrive at a generalized approach that can be used to solve both nonlinear and linear ODEs as well. Now the significance of this approach is that it has been extensively used in the computational framework to solve complex ODEs. So when you have complex ODEs of higher orders, this technique, and it is difficult for you to handle it analytically, to solve it using pen and paper, this technique has largely been employed to solve such ODEs. Now this technique is an approximation technique, so essentially it involves there are certain error associated with it. So therefore it becomes important for us to understand what is the nature of the order. Of course, when we discussed last time, in order to quantify this error is quite difficult, because the error, the way to quantify it, or the amount of the error that is introduced in an approximation depends on the function itself. This is something that we discussed about. However, it is possible for us to have a qualitative understanding of what is the error that is associated with the technique that we adopt. So the error when you use an approximation technique to solve an ODE, the error can stem from the function itself. When you fix a technique and you solve a function, the error can stem from the function itself. In the approximation technique, and when you adapt certain parameter to address or solve this ODE, you fix that the parameters, the corresponding parameters, and you adapt to solve this ODE through approximation technique because of the nature of the function itself. While for this particular approximation technique, for this parameter, a given function would give a good approximation, whereas a different function could give a bad approximation. So this stems from the function itself. So therefore, setting a quantitative value for a given approximation is not that straightforward. However, it is possible for us to qualitatively state that for this approximation function, the error will be of this range is possible. So this qualitative estimation of this error is where we will begin this lecture with. So ideally what we want to do is, we want to look into the techniques that can be adopted to solve a given ODE using approximation technique. As a starting point, we will revisit the technique that we already know, the approximation techniques that we already know, first to identify or qualitatively express what is the error associated with it. Quantitatively, it's quite difficult, but qualitatively, what is the error associated with it, we will try to address it. Now, the first approximation technique that we considered stems from the definition of the derivative itself. So the derivative, d of f of x, dx, the rate of change of this function with respect to x, can be expressed as x plus delta x minus f of x by delta x. So this is an expression that stems from the very description of the derivative itself. Now the approximation sign, it changes to an equal sign when we impose the limit delta x tends to 0. Now this approximation is what we refer to as the forward difference approximation. Now when you adopt a forward difference approximation, you fix the delta x value and then you find the derivative of a given function. For a given function, you will be able to arrive at an more or less close to the exact value. However, for a different function, for the same delta x, the approximation would cause a significant amount of deviation. So this deviation is primarily caused by the nature of the function itself. So therefore, the quantitative value cannot be attributed to the forward difference approximation. We cannot say when you use forward difference approximation, this would be the exact error associated with it. However, we will see that is it possible for us. We will see how can this error be quantified? How can this error be qualitatively expressed? So, because of course the forward difference approximation can also be used to identify the derivative of any function, not only linear but also nonlinear functions, and it has been adopted in the research activities as well. So therefore, forward difference also plays a critical role. So it is vital for us to understand how we can express the error associated with it. So in order to do so, in order to understand the error associated with such a function, we will consider the Taylor series expansion of, we will consider the individual term associated with this expansion. So we are not imposing this limit right now because we are not solving it by hand. So when you are solving it in a computational framework, when you are using a computation resources to solve this approximation, then you need to provide a definite value for the delta x. Now when you provide a definite value for the delta x, then you are rather relaxing this condition here. Now in such a case, when you have a definite value for delta x, even though that value might be close to 0, but you have a definite value for delta x, what it means is that you are adopting an approximation technique and there is a definite error associated with it, and that is what we are estimating, and that is what we need to qualitatively understand what is that error. So in order to do that, let us consider each of these terms that are associated with this approximation, a straightforward approximation. So we have the first term x plus delta x, and we will try to expand it using the Taylor series. Now the Taylor series allows us to expand any given function. So when you have a function f of x, the Taylor series expansion can be done when you consider a point A where you know what is the value of the function and also the derivatives. When you are able to handle a given function at a specific point A, and meaning when I say handle, you are not able to estimate the first derivative, second derivative or other derivatives, then the entire function can be expanded in terms of or using Taylor series. So correspondingly, we have a function A and we know the nature of this function at point, or rather we have a function f of x and we know the nature of the function at a given point A. So therefore, this function f of x can be extended as f of a plus the derivative of this function at the point A and the difference between the x minus a, the point that is known, and the variable. Now the second term would be the second derivative of, let me try to write it here, the second derivative of the function again at a and the difference square divided by 2 factorial and so on and so forth. So this is how we are able to expand a given function f of x at or based on a point A, and so this is referred to as the Taylor series expansion. Now let us try to do the same for x plus delta x. Now this x plus delta x, we know how it behaves, we know how this function behaves at a point x. So if we consider a point x and we know how this function behaves at a point x, then this function here can be expanded as f of x plus the first derivative of the function d of x plus delta x again at point x, and we have the difference, that is x plus delta x, and the known point is x here, so we have this term that is included along with the derivative, and the second term would be the second derivative x plus delta x again at x, and the difference term would be of this form here, the square of it along with the 2 factorial, so on and so forth. Now we can make this expression simpler. First of all, it is possible for us to cancel these two x's within this term. Here it is possible to cancel the x's, and also since we are estimating the function f of x plus delta x at x, we can replace f of x plus delta x with f of x. So correspondingly what we end up having is, so we are estimating f of x plus delta x at x, so therefore it can replace this term with f of x. So correspondingly the Taylor series expansion of f of x plus delta x can be written as f of x plus d f of x by dx delta x plus d square f of x by dx square delta x square. And since we have simplified the individual terms, we can now have a third term as well, d cube f of x dx cube, and again the more important 2 factorial delta x cube 3 factorial, and so on and so forth. Now we have an expression for, we have a Taylor series expansion of x plus delta f of x plus delta x, and now let us substitute this Taylor series expansion in this forward difference approximation. So the numerator of the forward difference approximation is f of x plus delta x minus f of x. So this is the numerator of the forward series expansion. So this numerator of the forward series expansion can be estimated from the Taylor series by just bringing this term over here. So when you do that, what you are left with is the derivative of f of x and delta x, the second derivative of the f of x, then delta x square 2 factorial, and so on. Now in order to complete the right hand side of the forward difference approximation, all we need to do is multiply both this term here by delta x. When you include or when you multiply this term by delta x, or rather 1 by delta x, then ultimately you would end up having approximating the forward difference. So when we do that, f of x plus delta x minus f of x divided by delta x, sorry, so when you multiply it by 1 by delta x or just divide it by delta x, what we end up having is, so when you do that to the left hand side, this the same needs to be repeated on the right hand side. Ultimately what we will end up having is d of f of x by dx plus d square f of x dx square delta x. Now that we are dividing it by delta x, so this term would get completely removed and the power of this term would get reduced. So therefore delta x by 2 factorial, and the third term, that is third derivative of the f of x would be delta x square by 3 factorial. So the power of the delta x gets reduced because we are dividing it by the delta x. Now this is the derivative that we are interested in. So all that we are doing is primarily because we need to know the first derivative of the delta x, and so we have now an expression for the first derivative of the delta x on the right hand side of the equation. But unfortunately, in addition to the first derivative of the f of x, what we essentially have is there are additional terms that are associated with it. So we have considered the forward difference approximation, and we have expanded the individual terms associated with it, and when we expand the individual terms associated with it, we see that in addition to the derivative that we are primarily interested in, there are additional terms that are associated with it, and these are referred to as the error terms. So these are contribute to the error when we approximate a given derivative using forward difference approximation. Now in these error terms, there is a dominant error. So we can identify a dominant error. The way we can identify the dominant error is, supposing we already have the condition that we need to introduce, we should have introduced, that condition is delta x tends to 0. So even though for the computational techniques, the delta x, even though it cannot be exactly close to 0, or it cannot be exactly equal to 0, so it will have a value that is somewhere close to 0. So it can be assumed to have a decimal like values. So when you assume such a case, then the dominant error comes from delta x. because the delta, as you increase the power of the delta x, the significance of the delta x will keep on decreasing. Of course, we have the reduction in significance through these decaying factorials as well, but nevertheless, since we are indirectly imposing the condition, that is delta x tends to 0, even though if I am not considering delta x is exactly equal to 0, but since delta x is close to 0, it means as the power of the delta x increases, the significance of the delta x to this entire expression, to this entire error, it decreases. So therefore, the dominant error term is this term here, and this the first term here, and the delta x contributes predominantly to the error. So therefore, this is the dominant error term. So this is the dominant error term. This is what predominantly contributes to your error. So ultimately, for forward difference approximation, in addition to our desired derivative, the error is of the order of delta x. So this is the dominant error term. So therefore, the forward difference approximation can be written as in this way, wherein the error is of the order of delta x. The dominant term is, so the dominant error is contributed by the delta x. Now, in that case, when you solve a specific function, now you are fixing up the function, and then you are using the forward difference approximation to solve the derivative of the function. Then in that case, depending on what is the value of your delta x's, correspondingly your error will get scaled. Let me repeat, we are not considering two different functions and using the same approach with two different delta x's or the same delta x's. Rather, in this case, what we are considering is we are considering a same function, a single function f of x, and we are using two different delta x's, and depending on the value of the delta x, the errors will be scaled. So this is the qualitatively we can state that for forward difference, the error associated with the approximation is in the order of delta x. Now, this is one of the approximation scheme that we have considered. Now, when you consider the other approximation scheme that we have looked into, it is the backward difference approximation. So it is backward difference approximation. The key, the dissimilarity between the forward and the backward difference is that in the backward difference approximation, the derivative is written as f of x, again approximately is equal to, or rather approximately it is f of x minus delta x divided by delta x. So this is the expression for the backward difference. Now that we have seen how we can handle such an approximation, to understand how we should treat such approximation to arrive at or to gain a qualitative understanding of the error associated with it, we will try to expand this function here, that is f of x minus delta x. If you try to expand it using Taylor series at the point x, it will be f of x again plus the first derivative of the f of x, d of f of x. So essentially it needs to be d of f of x plus delta x. Essentially this term should be d of x plus delta x divided by d of x, since at point x, and this, since it can be written as, this can be written as d of f of x plus dx, we have adopted the simplified version of it. So ideally the second term, the derivative, should be written in this way, but since we are focusing on a given point x, we have simplified it and written it in this manner. And the same way, the difference associated with it would be x minus delta x minus x. So this would be the difference term that is associated with it. So this would be x minus delta x minus x. But since, and so these two, x and minus can get cancelled out, and therefore we are left with minus delta x. In a similar way, when you consider this second term, second derivative of f of x with respect to x, and what you would end up having is minus delta x the whole square to factorial. So ultimately, for f of x minus delta x, the Taylor expansion of it would be f of x plus first derivative of the f of x, but since we have minus delta x here, so it can be written as the first derivative delta x, And since we have the square of the minus term, so the plus remains. So therefore the second derivative of the f of x at x, and this will be delta x square by 2 factorial. And finally, just to include, to show the trend, the third term will be minus because it's delta x cube, the third factorial of the f of x, and delta x cube by 3 factorial, and so on and so forth. So this is how the Taylor series of f of x minus expands. Now, when you consider the backward difference scheme and the numerator of the backward difference scheme, it begins with the numerator involves f of x minus f of x minus delta x. So in order to do that, all we need to do is bring this term here and all the rest to the other side, and when we do that, what we would end up having is again d of f of x by dx delta x minus d square f of x by dx square. So all that we are doing is bringing all these terms to the other side as we bring this term. So all these terms we are bringing it to the other side as we bring f of x minus delta x to this side. So therefore you have a minus sign, where initially it was a positive sign, now we have a minus sign. And the third derivative, and we have delta x cube by 3 factorial, and so on and so forth. Now, in order to have this term that is equal to that of the derivative with respect, or the approximation with respect to the backward difference, all we need to do is divide it by delta x. So we can take the delta x out and then divide it by this difference here. So we can take this delta x out from all these terms here and then divide it by this term, or bring it down. So we can take the delta x from each of these terms and then bring it to the other side. So when we do that, we end up with the expression that is characteristic of the backward difference, and that will be this, minus the second derivative of dx square delta x by 2 factorial, and the third derivative dx cube, rather delta x square by 3 factorial, so on and so forth. Now what we observe is, similar to the forward different case, this term, all these terms, they contribute to the error, and the dominant error is this term here, and it is in the order of delta x. So ultimately what we end up having is, we have this expression can be written as the first derivative, or the derivative when we estimate it using the backward difference, the error associated with it is in the order of delta x. So in both forward difference and the backward difference, the error associated with these approximation are in the order of delta x. Now depending on what your delta x is, correspondingly the error would scale. Now often while in materials research, often when you are trying to model a material's behavior, these are associated with, these derivatives are associated with the time derivative, or these are associated with how a system evolves with respect to time. So that is what we saw in our previous consideration as well. So when you write this expression for the nucleation rate, so when you consider the nucleation rate and write this expression, rewrite this expression for both forward and backward derivative. So in case of forward derivative, you have such an expression. So we'll write just for the forward derivative. When you write it for the forward derivative, what we end up having is, so what essentially we are considering is, we are trying to express what is the significance of this error in the real life situation. When you are handling a material's behavior, what is the significance of this delta x? So like we saw that usually when we are considering a material's behavior, we are considering the derivative with respect to time. So correspondingly the forward, so like the nucleation rate, so the forward difference for the nucleation rate would be of this form. When you consider estimating the nucleation rate using the forward difference scheme, it would be of this form here. d of x of t dt, and this would be of the order of delta t. So what essentially you are trying to do is, you are trying to find the nucleation rate by considering at different times. So we are considering the nucleation at different times. So what is the number of nuclei that is present at different time? So the time that you are considering is t, and the second time that you are considering is t plus delta t. So by comparing t and t plus delta t, the number of nuclei that are present in t and t plus delta t, you are trying to estimate the nucleation rate. Now in that case, the differentiation that you consider, the nucleation rate that you estimate by considering t plus delta t. So you have a system at t, and you consider the same system after a duration of delta t, and the system that you are considering is t plus delta t. Now in t, these are the number of nuclei that are present, and in t plus delta t, these many are the nuclei that are present. By comparing t and t plus delta t, you are about to estimate, or rather quantify, the nucleation rate. Now when you attempt to do that, the accuracy of your estimation of the nucleation rate when considering the forward difference or the backward difference is dependent on your delta t. So what is the significance of this error is, when you consider a given system at two different time steps, and there is a time width that is associated between these time steps, and based on these two different time steps, you are attempting to find the nucleation rate. So the smaller the distance between these two different time steps, the smaller the delta t is between the two different time steps, the smaller will be the error associated with the approximation. So what essentially we find is, the error scales along with the error scales with respect to the time difference that we are considering in order to estimate the nucleation rate. When the time difference that we are considering is smaller, then correspondingly you will get a good approximation. When it is higher, the error scales with this delta t here. So when we try to apply this error associated with forward and backward difference to a physical system, then what it essentially means is that the closer our observation is, the greater will be the approximation of our nucleation rate. The error associated with forward and backward difference is rather, it gets scaled up with the time distance, or the duration between the initial and the subsequent time that we are considering. Now let us try to find out if there is any other way of having such other similar approximation, but the scaling or the error associated with it is minimal. So let me repeat. What we need to have is, now the error is now scaling up with the delta t. The error that is associated with the approximation, it scales with delta t. It scales with, in a generalized case, it scales with delta x. And this delta x or the delta t is, often it is close to 0, so often like it assumes a decimal value. It is close to 0, even though it is not exactly 0, it often assumes a decimal value. So when we are able to have an approximation treatment wherein the error does not scale with delta x, but if it scales with delta x the whole square, then what essentially we have done is, we have significantly reduced the error associated with it. So when you have an approximation, and in that approximation the error scales with delta x, and when you want to refine this approximation, all you need to do is, you need to change the order of this error. So when your error is, instead of being scaling, or instead of getting scaled by delta x or delta t, if it gets scaled by delta x the whole square, then the lesser will be the influence, or lesser will be the amount of error that is associated with the approximation. When your order of the error, instead of being associated with delta x, instead of being related directly to the delta x, if it is related to delta x square, the smaller would be the significance of the error to the difference, or to the derivative that we are interested in. So let us see if there is any other approach that will give us such an approximation wherein our errors are not scaled according to delta x, but the higher order of the delta x. So when, say, your delta x is 0.1, your errors will be scaled according to 0.1. But if your you are trying to find an approach wherein the error gets scaled by delta x the whole square, then what essentially it means that this would be the order in which your error gets scaled. So for delta x, for an order that is of delta x, the error that got scaled by 0.1, now the error associated when you have a different technique, and the technique the error associated with that technique is of the order of delta x the whole square, then in that case the error associated will be significantly reduced. So what ultimately then we need is, we need an approach wherein the error associated with the dominant error term is of the order greater than 1. So of the order of, say for instance, delta x square, not just the delta x. So we need a technique wherein the error that should not scale with delta x, but it should scale with the higher order of delta x. Now, in order to do that, let us go back to our Taylor series expansion of the terms that we have considered, the Taylor series expansion of f of x plus delta x. So this we saw can be written as f of x plus the first derivative of the f of x delta x, the second derivative of the f of x delta x square by 2 factorial, and so on and so forth. And then we have also seen the Taylor series expansion of x minus delta x, that would be f of x minus the first derivative of f of x and the second derivative of the f of x and so on and so forth. Now, our goal is to have an approximation technique wherein the error associated with the approximation does not scale with respect to delta x, but it scales with respect to the delta x square. So in order to do that, let us try to rather consider these two Taylor series expansion, and we will try to rather, since this is what we are interested in, we are interested in to estimate the derivative, the first derivative of f of x. So since we are interested in first derivative of f of x, we will, if we add these two expansions, what we would end up having is we would end up cancelling the first derivative. So what can be done is we can subtract these two expansions, that is f of x plus delta x can be subtracted with the f of x minus delta x, and when we do that, when we rather subtract these two Taylor series expansions, what we ultimately end up having is these terms get cancelled and these positive and negative they sum up, and we would have 2 d of the first derivative terms delta x, and similarly the terms with the similar signs get cancelled out, and in the third term for f minus x delta x, f minus delta x is negative, so the third term remains, the third order delta x term remains, so therefore that term would be plus 2 third order derivative of f of x delta x cube by 3 factorial, and the third term would be 2 fifth derivative of f of x delta x 5 by 3 factorial. So all that we have, rather 5 factorial, all that we have done is we have considered the Taylor series expansion of x plus delta x, f of x plus delta x, and f of x minus delta x, and then we have subtracted these two, so that is f of x plus delta x minus f of x minus delta x. When we do that, the terms with identical signs, that positive signs, since we are subtracting, they get cancelled out, so f of x gets cancelled out, and the second derivative of the same positive sign, they get cancelled out, and since the third derivative is of positive and negative sign, they get doubled, and you have this term here, and the fifth derivative is of positive and negative sign, you have this expression, they remain, and you have this expression here, and ultimately this goes on forever. You will have the odd terms that assume a definite value in this way of or in this approximation or in this difference here. Now what can be done is we can take the 2 out and also the delta x out. So we can take on the set of terms in the right hand side of the equations, we can take the 2 and the delta x out. When we take the 2 and the delta x out and bring it to this side, what we would end up having is f of x plus delta x minus f of x minus delta x by 2 delta x. And ultimately, then this ultimately would lead us to the first derivative of f of x plus the third derivative of f of x but delta x square by 3 factorial, and the fifth derivative of the f of x power 4 delta x power 4 5 factorial, and so on and so forth. Now what we have then now arrived at is we have an expression that relates the first derivative. So this is the first derivative of f of x that we are interested in, and these are the associated error terms. So these are the associated error terms, and these are the first derivative of the f of x. Now when you consider this associated error terms, this is the dominant error term, and this dominant error term is of the order of delta x square. Now what we have essentially done is we have now a way of estimating the first derivative, and this approximation technique of estimating the first derivative involves an error associated with it. There is an error associated with it, but this error is of the order of, this error that we have found is of the order of delta x square. So when you consider the forward difference and the backward difference, the error was of the order of delta x, but here in case of this technique, the order is of the error is of the order of delta x square. So what it essentially means is that we have significantly reduced our error by this new approximation technique, and this technique is referred to as the central difference. So what central difference does is it rather changes the order of the error or the order of the dominant error, and instead of being associated with delta x, now the order of the dominant error is delta x square, it's 2, and correspondingly your error gets reduced. So therefore, when you are attempting to approximate the first derivative of a given function, when compared to the forward and backward difference, the central error associated with the central difference will be significantly lower. It will be an order lower than the forward or backward difference scheme. Now this is the central difference approach. This is commonly adopted when solving complex derivative complex ODEs, and this central difference approach is adopted because it gives us a minimal error. The order of the error is rather reduced when you use, it's reduced by 1 when you use central difference scheme when compared to the other approximation like forward and backward difference. And the way of estimating the central difference or employing the central difference for a function f of x. So if you have a function f of x and you want to find a derivative for the function, so this is what you need to do. You need to consider 2 time step. In addition to the x, you need to consider a forward time step, that is x plus delta x, and need to consider a backward time step x minus delta x, bring it together in this manner, and then you would then be employing central difference scheme to approximate the derivative of the function f of x. And when you use central difference, the order of the error associated with the approximation is reduced by 1. So you have reduced an order of the error that is the approximation involves. Now one elegant feature of this approximation technique is that not only the first derivative but higher order derivatives can also be estimated from these different schemes, from this approximation scheme. So using the central difference approximation scheme, not only the first derivative but also higher order derivative can also be approximated. Now that approximation, again, in order to understand how the higher order approximation can be rather achieved from the central difference, it all again stems from how we are considering or how we are handling the expansion of x plus delta x and the x minus delta x. So when you write the expansion of x plus delta x as something like this, dx, the second derivative. So this is something that we have been writing for a while now, 2 factorial, and the third term, the third derivative of f of x, correspondingly the delta x cube, 3 factorial, and so on and so forth. And the f of x minus delta x will be of this form, delta x, and the second derivative would be and the third term would be the third derivative of f of x with respect to x, so on and so forth. Now, in order to find the first derivative, we took the difference between these two expressions. But when our interest is to find the second derivative, then we need to ensure that this term doesn't get cancelled out. So what we need to do is we need to sum these two terms up. And when we sum these two terms up, that is, instead of taking the difference as we did for the central difference, when we sum these two up, so x plus delta x plus f of x minus delta x, then what we would end up having is this would be equal to 2 f of x, and in this case these two terms gets cancelled out, then rather plus 2 the second derivative of the f of x, and we have delta x square by 2, and the third term gets cancelled out, and the fourth term exists, so it will be the fourth derivative of f of x by 4 factorial, and so on and so forth. Now it is possible for us to rather cancel these two and then bring this term here. So we can bring this term to this side, so it will be f of x plus delta x plus f of x minus delta x minus 2 f of x. So we are bringing this term here, minus 2 f of x, and then in addition to that, it is possible for us to take the delta x square term as well out. So when we take, you bring this to this side, and if you take delta x square term out and bring it to this side, what you would end up having is, so we are, in addition to bringing the 2 f of x to this left hand side, we are also taking, once you bring this to your left hand side, all the terms would have this delta x square term common. So it is possible for us to take this term as common outside and then bring it to the denominator. So what you would end up having is the second derivative of f of x plus the 2 remains the same, fourth derivative of f of x by delta x square by 4 factorial, and so on and so forth. Now what we have achieved is, using this expression, so using this expression here, we will be able to approximate the second derivative of the function of f of x. So this second derivative of the function of f of x can be approximated by or through this function here. Through this expression here, you will be able to approximate the second derivative of f of x. And now when you consider the error associated with such an approximation, the error stems from the series of terms, and this error is of the order of delta x square. And when compared to delta x, this error is an order less. So what essentially we have now is, we have now, in addition to having an approximation for the first derivative, we now also have an approximation for the second derivative. Starting from this Taylor series expansion of f of x, x plus delta x and x minus delta x, we will also be able to estimate the third derivative, fourth derivative, so on and so forth. All the higher order derivatives, like we have approximated for the second derivative, can be extended for the higher order derivatives as well. So what essentially we have done is, by considering the forward difference, backward difference, and by considering the terms associated with the individual term associated with the forward difference and backward difference, we were able to estimate, or we were able to express the error associated with each of these approximation. And by combinedly considering the terms that are associated with forward and backward difference, that is f of x plus delta x and f of x minus delta x, by combinedly considering it, we were able to arrive at a new approximation scheme called as central difference scheme. So initially, we treated forward and backward difference separately to identify what is the order of the error associated with it. So forward and backward difference scheme, both these schemes, the error associated with those schemes are rather similar, and they are of the order of delta x. When you consider the central difference scheme, the central difference scheme considers, or it encompasses the terms associated with forward and backward difference. So there are specific terms associated with these schemes, and the central difference considers both. And when it considers both, the error is reduced by an order, and the error is associated with the central difference scheme is of the order of delta x square. Now finally, using the combination of the terms that are associated with forward and backward difference, that is f of x plus delta x and f of x minus delta x, the Taylor series expansion of it, now it is possible for us to estimate or to approximate higher order ODEs. Now by considering the approximation of x plus delta x and x minus, or Taylor series expansion of x plus delta x and x minus delta x, it becomes possible for us to estimate the higher order ODEs. So all stems from the Taylor series expansion of these two functions, x plus delta x and x minus delta x. So with this, we will wind the structure up, and we will try to build on this understanding in the subsequent lectures. Goodbye.